Hello friends, so today we are going to solve questions from Heat and Thermodynamics, and these questions are from the year 2001, 2003 and 2004. From year 2001 there is one question, from 2003 one question, and from 2004 we are having 3 questions. So in total we are going to solve 5 questions. So first question, it was asked in the year 2001, and it states that a 5-meter long cylindrical steel wire with radius 2 into 10 to the power minus 3 meter is suspended vertically from a rigid support and carries a bob of mass 100 kg at the other end. If the bob gets snapped, calculate the change in the temperature of the wire ignoring losses. For the steel wire, Young's modulus is 2.1 into 10 to the power 11 pascals, density is 7860, and specific heat is 420. So in this case, we can just draw our approximate diagram, and then we are going to solve this. In this case, we have to remember that is basically a conservation of energy. So amount of energy that will be, you can say, gained when the wire is going to snap will be converted into the heat energy of our this wire. So the basic diagram is, so we have a wire, and to the other end of the wire there is a bob. Okay. And let us suppose L is the length of the wire, and we are given, okay, this is little bit, wire is little bit thick, having some radius, and R is the radius of the wire, and we have, we can say, density of the wire, rho is the density of the wire. Okay. So let us write it as it is. So we are given length of the wire, L will be our 5 meter. We are having radius of the wire, radius of wire is suppose our R, which is equal to 2 into 10 to the power minus 3 meters, and we are having density of the wire, density of that is a rho is equal to 780. kg per meter cube. And Young's modulus and is also given to us. So we can say Young's modulus represented as Y will be equal to 2.1 into 10 to the power 11 Newton meter square, and specific heat of the wire is also given to us. Specific heat, that is S, is given as 420. Okay. So first of all, we are going to find out the mass of the wire, and then we are going to calculate the potential energy, or we can say elastic potential energy stored in the wire, and that will be equal to our, you can say, when it gets snapped rather, wire gets snapped, this potential energy will be utilized in raising the temperature of the wire. So first we are going to find out the mass of the wire. Mass of wire, that is small m, will be equal to density into volume and density is given to us. Density is 7860 and volume is our pi r square L. So from here we get this as 7860 pi, and radius is our 2 into 10 to the power minus 3 whole square, and length is given to us as 5 meter. So from here we get our mass is equal to 0.494 kg. And now we can easily find out the elastic potential energy stored in the wire. Elastic potential energy stored in wire, and suppose that is represented as capital U. Therefore we can write this, our U will be equal to our half, it will be our stress multiplied by strain and multiplied by volume. And we substitute their respective formulas. We get this as half, stress will be equal to our mg and divided by pi r square. Strain will be our change in length, original length, and volume is our pi r square times L. And from here this pi r square, L length and length cancels out, and this gives us our half mg multiplied by delta L. Okay. And delta change in length is not given to us, so we are going to convert this into as our Young's modulus of elasticity. Therefore we can write our U is equal to our half, and this comes up mg, and in place of delta L we can write this as our mgl, and we have our pi r square multiplied by Young's modulus y, which can be further simplified as our m square g square L, and we are having pi r square multiplied by y. Now we can just substitute the values. We get U is equal to half, and here capital M is the mass of the bob, that is of 100 whole square. G we can take as 10, and length is given to us as 5 meter. Pi, radius is our 2 into 10 to the power minus 3 whole square Young's modulus is given to us as 2.1 into 10 to the power 11. So we get this energy will be equal to 0.9478 joules. Now we can use the conservation of energy. Conservation of energy, and that conservation of energy gives us that our, we call this as elastic potential energy. Elastic potential energy is equal to rise in the temperature and from here we can write that our U is equal to M specific heat multiplied by delta of T. So we simply substitute the values. We get this as delta of T will be equal to our U divided by mass and specific heat. U is our 0.9478. Mass is given to us, mass we found out rather is 0.494. Specific heat is given to us as 420. So this rise in temperature comes approximately equal to 4.56 into 10 to the power minus 3 degree centigrade. Next question. It was asked in the year 2003 and it states that the PT diagram for an ideal gas is shown in the figure where AC is an adiabatic process. Find the corresponding PV diagram. So basic PT is given to us and it is mentioned that our AC is adiabatic. So at least from here we can say that for A, if our pressure is our AB will be our isothermal because it is at a constant temperature, and our AC is said to be our adiabatic. Okay, so let us start from our PT diagram, then we come to our requirement of our PV diagram. We have to, you can say, juxtapose the both the things. So we start with a PT diagram. And PT diagram, we know that our AB is isothermal. AB is our isothermal, and so from our ideal gas law we can write this as PV is equal to nRT, and temperature will be constant, therefore we can write from here that P is inversely proportional to our volume V. Okay, so it means on our this PV diagram, okay, and later on we can just merge into PV diagram. And secondly, we are given that AC is our adiabatic. We are given that AC is our adiabatic, and from there we can write that our PV raised to power gamma is equal to constant. Okay, and for gamma we know that is our Cp upon C of V, and if we use our ideal gas equation we know that our PV is equal to nRT, and from here we can also write that the TV gamma minus 1 is equal to constant, or we can also write it as our P1 minus gamma T raised to power gamma is equal to constant. So we can use this, from the PT diagram. Okay. Now we come to our you can say PV diagram. So it means we need to translate the PT process into PV space. Okay, and we have to remember that for our PT, let's make, and it is given as, okay, it's not mentioned here. Therefore, our AB, which is our isothermal process, and isothermal process for our AB, so we can write our on PV, we can write our P times V, or let me write it directly, we can write our P is equal to nRT upon V. Okay. So therefore we can say that P is inversely proportional to our volume, and this will be giving us, you can say, a curve which will be something like a hyperbolic. Okay. One second. Let me do it by using notations, will be much more better otherwise. Okay, let me do it otherwise. So let us say that we have our point A, and for point A we are having pressure of PA, temperature of T1, and volume of our VA, and we are having our point B, and pressure is our PB, temperature T1, and volume is our VB. Okay, and A to B is our isothermal. Okay, so we can write that our T1 is basically constant, therefore we can say that our PA VA is equal to PB VB. Okay, and our and if we assume it to be our expansion, so we can say that for expansion we can write that our VB is greater than our VA. One second, it doesn't look good actually. This is our PA and this is our PB, and corresponding volume is our VA, and here we having VB. Okay, so PB is less than of PA, so it will be reverse. I think this looks good. Therefore we can say that our PB will be less than our PA. Okay, and for point C, let us write this as our PC, TC and VC, and our AC is adiabatic, so we can say our AC is our adiabatic, so we can write our PA VA raised to power gamma is equal to PC VC raised power gamma, or in terms of temperature we can write this as our TA VA gamma minus 1 is equal to TC VC gamma minus 1, and we have assumed that at A temperature is T1, so we can say that our TA is equal to T1, and our this is our temperature T1 and this is temperature TC. So from here we can say that our TC is greater than T1. TC is greater than our T1. It doesn't look. Or I'm not. One second. Is there any other way? Because it is not mentioned how it is moving, but at least we can say that it doesn't look good actually. It has to be done in other way. It is not looking good. We can do it by using directly, I think. Because it says that AC is adiabatic, so it should be going like this from C to B, and it should be going from B to A, cyclic. And if it is going from B to A, then this doesn't hold. Isothermal is there and it is expansion, so VA is greater than VB. Or we can use this as area under the curve. I think that will be much better. Let's do it by considering the area part. That will be I think let's do it directly. It is not A to C, C to B, and B to A. B to A is our expansion. So if it is expansion, then VA will be greater than VB. Then VA is greater than VB, and PB will be greater than I think it is somewhat okay. Let's do it by area. It is little confusion otherwise. Not helping. we can just do it by the slope method. That will be much more better. It is not. So we can just do it 1:1, and okay. So we know that our AB is our isothermal. So we have already written that, and we have AC is our adiabatic. Okay, and here we can also say that it is basically a expansion, and for expansion process the slope of adiabatic curve is more. Okay. Or we can also say in terms of area, we can also write that area under PV for isothermal process is more than adiabatic. Okay. And more than adiabatic process for the same increase in the volume. For the same increase in the volume. So if we check the area wise, the only option that come close to, because option that will be the correct one will be our option number B. Okay. So we have option B is correct. It should be actually okay. And we can also okay, let's move to the next question. It was asked in the year 2004, and it states that one end of a rod length L and cross-sectional area A is kept in a furnace of temperature T1. The other end of the rod is kept at a temperature T2. The thermal conductivity of the material of the rod is K and emissivity is E. It is given that T2 is equal to Ts plus delta T, where delta T is much smaller than Ts, being the temperature of the surrounding. If delta T is proportional to T minus Ts, find the proportionality constant. Consider the heat is lost only by radiation at the end where the temperature of the rod is T2. So basic figure is given to us. We have a furnace with temperature T1 and there is a rod. One end of the rod is at temperature T1 and other end is at the T2. And it is said that the heat is lost only at this end where the temperature is T2 and Ts is the temperature of the surrounding. Okay, so that is given to us. So in this case, let us consider a axis. So this is our x-axis and this is our y-axis. So this point is our origin, which we call that x is equal to 0. So other end will be equal to our x is equal to capital L. Okay. So we can say that our length of the rod is capital L and area of cross section is our A, and one end we have assumed is at x equal to 0. So we can say one end is x equal to 0 and this end is at a temperature of T1, which is nothing but the temperature of the furnace. And we have our other end. So one end, let us call this as end A and this as end B. So one end means end A. Well, let's not call this A. Let us call this as P and Q. This is P and this is Q. So this end we are calling as P. And we have other end. Other end is our Q and that end is our x is equal to our L, and the temperature of that end is given as T2, which is equal to our Ts plus delta T. Okay. And the rest of the things are given to us, and we have to remember that the heat lost will be only from the end Q. Okay. There is nothing about the and in this case we are supposed to find out our proportionality constant. Okay, so we can say that our at steady state the heat conducted by the rod at will be heat dissipated by the, or we can say heat radiated by the rod. So we can just use the principle which states that in steady state heat conducted through rod is equal to heat radiated from end that is our Q, and at temperature T2. So we can write the respective formula. The heat conducted through a rod, it can be represented as our K times A, difference in the temperature divided by length L, and that will be equal to our the radiated, which will be our emissivity A and Boltzmann constant, and we have this as T2 whole raised to power 4 minus the surrounding whole raised to power 4. We are given that our delta T is very much less than our Ts. Therefore, we can write that our T2 raised to power 4 minus Ts raised to power 4 can be approximately equal to 4 times Ts whole raised to power cube, and this is our delta T. Okay, so we substitute it, we get this as our Ka T1 minus T2 upon L is equal to 4EA and sigma, and we are left with our Ts cube, and we have our delta T. Okay, and we can cancel out our A, and we are also given that our T2 is equal to Ts plus delta T, that is given to us. So we substitute it, we get this as our T1 minus, this comes as a Ts minus delta T multiplied by K upon L is equal to 4E, and we have here Ts cube and delta T, and we can shift delta T to our right side, and we get this as T1 minus Ts, and let's multiply by L also. So this comes as K will be equal to delta T, we can take as common, and this will be 4E sigma Ts cube, and this will be our plus of K multiplied by L. Therefore, our delta T will be equal to, we get this as our K T1 minus Ts divided by 4E sigma Ts cube plus K and multiply by our L. One second, I think there is some, oh yes, K, L will not be multiplied, so L will be multiplied by here, then it will be added to K. Okay, so this is our L is being multiplied by here, and we are given that our delta T is proportional to T1 minus T minus, okay, it should be actually T1 minus Ts, T1 minus Ts. So if we make comparison, we can write that proportionality constant will be equal to our K divided by 4E sigma Ts cube times L plus K. So this is our proportionality constant. Next question. was asked in the year 2004, and it states that the piston cylinder arrangement shown contains a diatomic gas at a temperature of 300 Kelvin. The cross-sectional area of the cylinder is 1 meter square. Initially, the height of the piston above the base of the cylinder is 1 meter. The temperature is now raised to 400 Kelvin at constant pressure. Find the new height of the piston above the base of the cylinder. If the piston is now brought back to its original height without any heat loss, find the new equilibrium temperature of the gas. You can leave the answer in the fraction. So, in the first part, it is basically a constant pressure process. And based on this, we have to find out our new height. So we can write a new height of the piston, new height of piston at constant pressure, at constant pressure. Therefore, we can say from our ideal gas law, we know that our PV is equal to nRT. So if pressure is constant, therefore we can write that our V upon T is equal to constant. And from here we can say that our V1 upon T1 is equal to V2 upon T2. And we can define this V1, T1 and T2. So here T1 is our initial temperature, which is given as 300 Kelvin. T2 is our final temperature, which is given as 400 Kelvin. And initial height is suppose H1, initial height of piston. Let us suppose that is our H1 is our given as 1 meter, and we are also given the cross-sectional area of the cylinder. Cross-sectional area of cylinder, that is our A, which is given as 1 meter square. So we can find out the volume of gas inside the cylinder. Therefore we can say that general formula we can write as volume of gas. If we represent it as our V, then V will be equal to area multiplied by the height of the piston. And area we know is 1, which is not going to change, so this will become as equal to H. Therefore, we can divide that our initially V1 will be equal to H1, and we can also say that our V2 will be equal to H2. Here H2 is our final height. And we have written, or we can find out the ratio. So we can say V1 upon V2 is equal to H1 upon H2. And V1 upon V2 is equal to T1 upon T2. We can write it from here. V1 upon V2 is equal to T1 upon T2. So this comes equal to T1 upon T2. And T1 is our 300 and T2 is our 400. So this 0 goes away and this comes as our 3 by 4. We need to find out our H2. Therefore, we can write that our H2 will be equal to this will be over 4 by 3 times h1. h1 is given as 1, so we get our h2 is equal to 4 by 3 meters. So this was our first part. Second part is says that it is brought back to original height, which was h1 without any heat loss. Okay, so basically which is our adiabatic process, and we have to find out the new equilibrium temperature of the gas. So we can say new equilibrium temperature and let us call this as T3, and it says that there is no heat loss, therefore process is adiabatic. Okay, so we can say no heat loss, therefore Q will be equal to 0, or we can say our adiabatic process. And we know that for adiabatic process we have our TV gamma minus 1 is equal to constant, and for adiabatic process our T2 will be now our initial temperature, okay, because it is going to start from the first part. So T2 will be our initial temperature and T3 will be our final temperature. Okay. Similarly, V2 will be our initial volume and V3 will be our final volume. Okay. So we can say that temperature is our T2, which is our 400 Kelvin. We can find out our V2. V2 is our equal to H2, which is 4 by 3 meter cube. Okay. And this is our initial state now. So we can say this is our initial. And we can find out our final. Final will be our, suppose volume is our V3. So V3 will be equal to, because it says that it has to come to the same height, so that will be our H1 multiplied by A, giving us H1. Okay. And temperature, let us suppose we have said that is our T3. This is our T3. Therefore, we can write the equation that our T2 V2 gamma minus 1 is equal to T3 V3 gamma minus 1. So we are interested in about T3. So T3 will be equal to T2, and we have our V2 upon V3 and gamma minus 1, and the gas is given to us as our diatomic. So we know that the value of gamma will be equal to our diatomic 7 by 5. So we can say our gamma will be equal to 7 upon 5. So let's substitute the values. We get this as our T3, T2 is our 400, and our V2 is 4 by 3, and V3 is our H1, which is our 1 meter. So this comes as 1 whole raised power gamma minus 1, that is our 7 by 5 minus 1. So this comes as our 400 multiplied by 4 by 3 whole raised to power, this will be coming as 2 by 5. And we can approximate this will be equal to 448.8 Kelvin. This is a final equilibrium temperature. Next question. It was asked in the year 2004, and it states that a cube of coefficient of linear expansion alpha s is floating in a bath containing a liquid of coefficient of volume expansion gamma L. When the temperature is raised by delta T, the depth up to which the cube is submerged in the liquid remains same. Find the relation between gamma S and gamma L, showing all the steps. So in this case, even though the temperature is raised by delta T, the depth up to which cube submerged in liquid, it is going to remain same. Okay, so that is important part here. Okay. So it basically means that okay, so we can say that cube is floating so if cube is floating, so it means will be in equilibrium, and we have to also keep in mind that the depth to which it is submerged does not change when the temperature rises. You can say the depth up to which cube is submerged remains same. When temperature rises by delta T. And we have to remember that the coefficient of linear expansion, that is alpha s, which basically means that the length changes with temperature. Length changes with temperature. And for gamma L, which is volumetric expansion coefficient, and which means that volume or we can say density changes with temperature. Okay. And it is submerged and it is floating, so everything will be in equilibrium. Okay. And in this case, the rest of the things are given to us, but we can assume that the density, okay, let's discuss first of all cube. And cube is given to us as side length at initial temperature. At initial temperature is about L, and coefficient of linear expansion is given to us. Let's write its density. density at initial temperature, let us call this as rho s. Okay, and now same thing we are going to write for liquid. Liquid, we can say density at initial temperature that is our rho L, and coefficient is given to us, so we are not bothering to write it. And initial temperature we assume that is our T. Initial temperature we assume is T, and increase in temperature, or we can say temperature increase, is our delta T. And let's assume that initial submerged depth is H. Initial submerged depth is, let us suppose, is our H, and this value of H will be going to lie between our 0 and L. Okay, so when H will be equal to L, so basically entire block is submerged. Okay, but it is said floating, so we are going to assume only partial submersion. Okay, and this was our initial condition, but for the final condition, the submerged, you can say final condition, the submerged depth is still our H. Rest of the things we have already mentioned. Okay, so as the cube is floating, so therefore we can say that the buoyant force will be equal to the weight of the cube. Okay, this is the basic Archimedes principle. So we can say initial floating condition we can write that weight of cube let us suppose that is our W, will be equal to its mass multiplied by G, or we can say density multiplied by volume multiplied by G. Initial volume, that is our of the cube, we can say that our Vs will be equal to our length L cube. Therefore we can say our weight is equal to rho s L cube multiplied by G. And we know that the buoyant force is equal to amount of liquid displaced. And we know that buoyant force is equal to amount of liquid displaced. And we said that only h height is submerged in the liquid. Therefore, we can find out that the submerged volume let us call this as V submerged will be equal to our L square multiplied by height h. Okay. And therefore the buoyant force, and let us call this as buoyant force as Fb. So we can say our buoyant force Fb will be equal to density of the liquid volume submerged multiplied by G. So the density of the liquid, and this comes as L square H multiplied by G. And in equilibrium, at equilibrium, our weight will be equal to buoyant force. Therefore, we can say density L cube G will be equal to density of the liquid L square H multiplied by G. Here G and G, this L square goes by the cube. Therefore, we get the height H will be equal to this will be density of our cube, density of the liquid multiplied by the length L. So this is the height that is submerged. Okay. Now we are going to find out the submerged fraction. So submerged fraction, we can just find out the ratio. So we can say the submerged fraction will be equal to F H upon L, which will be coming the ratio of their density for our cube as well as liquid, which is in general our ratio of their densities. And now we come to the when the temperature is raised. So we can say effect of temperature increase. Effect of temperature increase. Okay. And this temperature is increased by delta T, and obviously this increase in temperature is going to affect both cube as well as liquid. Okay. So this will be affecting our cube and liquid. In cube there will be a linear expansion, as well as in liquid there will be a volumetric expansion, or we can say it will be affecting their densities as well as dimension. Okay. So we can say from here that affecting densities, their densities and dimensions. Okay. But this H is going to remain same. Okay. Depth is same, but obviously the cube side length is going to change. Okay. First of all, let's discuss our cube expansion. So cube expansion, we are given that coefficient of linear expansion is given to us. So we can write the fractional change in length per unit temperature. Fractional change in length per unit temperature. That is our delta L. Length we have assumed capital L. Okay, so let me write this as delta L will be equal to our linear expansion, the original length, and multiply by the change in temperature. Therefore, we can see from here that our new side length that is our L prime will be equal to L, and this our standard formula, linear expansion multiplied by change in temperature. As the length is going to change, so obviously its volume is also going to change. So we can say new volume is our V prime will be equal to, let us call this as Vs prime, and this cause L prime whole cube will be equal to L 1 plus coefficient multiplied by delta T, and this will be whole cube, so let us keep this will be cube and this will be also cube. And this coefficient product ideally is very small. Okay, therefore we can approximate that our 1 plus alpha s delta t whole raised power cube is approximately equal to 1 plus 3 alpha s multiplied by delta t. Okay. Therefore we can say that our Vs prime will be equal to approximately equal to our L cube, and this has 1 plus 3 alpha s multiplied by delta t. Okay. And we know that the coefficient of volume expansion is approximately equal to 3 times our linear expansion. So we know that coefficient of volume expansion, which is given to us as gamma of s, is approximately equal to 3 times alpha of s. Therefore we get Vs prime will be equal to L cube 1 plus gamma s multiplied by delta t. Okay. Now we can find out the new density because mass is going to remain same. Okay. Therefore we can say new density let us call this as prime is equal to ms upon Vs prime. Ms is going to remain same, so this comes as rho s L cube divided by L cube 1 plus gamma s multiplied by delta t. Here L cube and L cube cancel out, so we get this will be equal to our rho s 1 plus gamma s multiplied by delta t, and binomially we can approximate the equation that our new density will be equal to our rho s 1 minus gamma s times delta t, and we can just substitute in terms of alpha also, so we can say this is approximately equal to rho s 1 minus 3 times alpha s times delta t. Now we come to the liquid expansion. Cube expansion, and we come to the liquid expansion. And for liquid expansion, we are given that its volumetric expansion is gamma L. Therefore, we can say new density is our gamma L prime will be equal to our original density and divided by 1 plus volumetric expansion multiplied by delta T. And similarly, we can write it as using binomial. New density will be equal to our original density and 1 minus gamma L multiplied by delta T. Now we can find out the new submerged volume. New submerged volume. And for new submerged volume, first of all, let's find out the new area, new cross-sectional area rather. So we can say our new cross-sectional area that is our A prime will be equal to our L prime whole square. And we can write this our A prime will be equal to L prime. We already know L prime is our L plus alpha S delta T. So this comes as our L square 1 plus alpha S delta T whole square, which can be approximately written as L square 1 plus 2 alpha S multiplied by delta T. But the height is, it is said that it is remain same, the submerged height. Therefore we can say our new submerged volume, new submerged volume, that is our V prime submerged, will be equal to new area multiplied by the height, which is same. So we get this as our volume new submerged will be equal to our L square 1 plus 2 alpha S multiplied by delta T multiplied by H. Now we come to our new final floating condition when the temperature is increased. So you can say final floating condition obviously the weight will be balanced by the buoyant force. The condition is going to remain same. So we can say that our S prime Vs prime multiplied by G will be equal to, for our liquid, volume submerged new and multiplied by G. Here G and G goes away and we substitute rest of the values. So we get this as submerged and new volume is our L prime cube is equal to, and this is our rho L prime submerged we found out is our L square multiplied by 1 plus 2 alpha S delta of T and multiplied by H. And we can substitute, this is our prime, so we can substitute our L prime we know. Let's substitute all the values, and this rho S prime is our rho S 1 minus 3 alpha S multiplied by delta T, and our L prime is our L plus alpha s whole cube. Okay, or we can just substitute our volume also, that is one and same thing. So let us write in the volumetric form, that is our L cube, and 1 plus this is our 3 alpha s multiplied by delta t, and we can write equal to, this comes as our, for liquid we can say this as density for the liquid 1 minus, it was 1 minus gamma L delta of T, gamma L delta of T, and rest thing is going to remain same, that is our L square 1 plus 2 alpha s delta of T and multiply by H. And if we see our left hand side, so if we multiply them, we are going to get this as rho of s L cube, and this will be coming as 1 minus 3 alpha s delta of T, and this will be going plus 3 alpha of s delta of T. Okay, anything else is left? 1 and this will be our minus 3 alpha of s delta T whole square, and this term, because it is very small, so we are going to neglect it, and these two terms cancel out. So let me say this is our left hand side, which comes as our rho s multiplied by L cube. Okay, so this portion we are ignoring, okay, neglecting. So this comes of left hand side. Similarly, we can solve our right hand side. So right hand side is our rho L multiplied by L square, and we get this as our L square H, and we have 1 minus gamma L multiplied by delta T, and this is our plus 2 alpha s delta of T, and this comes as 1 and this is 2. Okay, and this will be minus 2 gamma L alpha s and delta T whole square. Okay, and this term, once again, this we are going to neglect. Okay, so we get our right hand side will be our rho L square times H, and this will be 1 minus gamma L times delta H plus twice alpha s multiplied by delta T. Now we can just equate them. Okay. So we get that our rho of s L cube is equal to rho of L square H, and this comes as 1 minus gamma of L delta t plus twice gamma of s multiplied by delta of t. And we know that our I think we already calculated initial condition is our we calculated I think I forgot to mention one step. Okay, no problem, we can just this is our initial condition. Okay, this portion we are going to use this part g, we can just cancel, so let me write it here. So we can say from initial condition we can say that rho of s whole square whole cube volume is equal to the displaced, which is rho of L square times h, and therefore we substitute it, we get this as our rho of s L cube is equal to rho of s L cube 1 minus this is about gamma L delta of t plus twice alpha s delta of t, and here these two terms cancel out, so we get this as our 1 is equal to 1 minus gamma of L delta of t plus twice alpha of s delta of t, and here also this 1 and 1 cancel out. Therefore from here we get this will be our gamma of L delta of t is equal to twice alpha of s delta of t, and obviously delta of t cannot be equal to 0. Therefore from here we can write that our gamma of L is equal to twice alpha of s. This is our final relationship. Okay. I think so this gives the relationship between the linear expansion as well as the volumetric expansion. So this completes the questions. Thank you.